Hello everyone. Today we'll talk about the solution of the problem take k of each character from left and right. The first thing that we should notice, which is pretty obvious, but it's good to point it out, is that while it's possible for us, while taking the leftmost or rightmost, each minute, each step, to take sometimes from the left, then maybe from the right, then again from the left, then again from the right, so to interweave taking from the left and taking from the right, but the order in which we take elements doesn't really matter. And it might be convenient for us to think about taking all the elements from the left together and all the elements from the right together. And however we think about it, the final result is that we've taken some prefix, maybe empty, and some suffix, maybe empty. And we want to take the minimum number of elements, so we want to find the pair of prefix and suffix, such that every character ABC appears at least k times within both the prefix and suffix taken together, and their length is minimal. Okay, so this is a simple observation, but okay, we have a problem with taking a pair of prefix and suffix that do not overlap, and first of all, it's often possible, or sometimes it's more convenient, sometimes it isn't, to think about selecting a prefix and suffix pair as the same thing as selecting a subarray, because then what remains is a prefix and suffix that do not overlap. So this is a very standard pattern, and maybe it'll be useful for you to think about it as a subarray. I'm going to be thinking explicitly about prefixes and suffixes, but either way, for those two equivalent dual formulations, there is often a possibility of using two pointers, in that we can, because two pointers is very natural for the subarray, because we'll be pushing forward the left end of the subarray and operating on the right end of the subarray. We can use two pointers here, because we only lose elements from the left and gain elements from the right, so we always benefit from adding elements, and removing elements can only hurt us. And of course that two pointers technique can either be implemented based on those subarrays or based on prefixes or suffixes. And the final algorithm, of course, is that we'll be trying all the prefixes, and for every prefix we want to find the shortest suffix such that they together give us what we need, at least k of all of those letters. And when we are looking at shorter and shorter prefixes, we're going to be needing longer and longer suffixes. So this is the standard two-pointer pattern. And the code for that implementation, that straightforward implementation, is this. We can first of all create an if for k equal to 0, because then the answer is 0. We don't have to do anything to have at least 0 of all the letters. Otherwise, we'll want to maintain the count of all the letters, how many letters we have of every type. So we can define letters as ABC. Remember the length of the string. Now, to create the counts, we can use syntax like this. So this is a dictionary comprehension. This is a dictionary that for every C gives us the value of 0. And C ranges over letters. Letters is a string. We can write for C in string. So this will be ABC, very useful in Python. And now we'll be calculating the shortest prefix that by itself contains at least k of all letters. Notice that either such a prefix exists or it's impossible to solve the problem, because at the end we're going to be checking the prefix of the whole string. And if that's not enough, then the whole string is not enough. So we'll be going for I, and of course the range of the length of the string, increasing the counts. And now the benefit of writing it as prefix and suffix is that our requirement is that minimum count is at least equal to k, which in practice means it's equal to k. If we're looking at a subarray, then instead of looking at prefix and suffix where every character appears at least k times, we would have to have a subarray where each letter appears at most the count in the whole string minus k times. And this type of condition will be, well, it wouldn't be more difficult, because we can then subtract from the counts, but it's a bit more of a complication, though it's not really a complication. And now we want to be sure that we found such a prefix, so that we've broken out of the loop. So again, Python to the rescue, we can write for else. And so else is after we've exited for, by range running out, but without a break. Without a break, that means that there is no good prefix, we can return -1, and we are done with this case. So again, nice use of Python. And now our result is equal to I plus 1 because we've taken all the elements up to element at index I. So we've taken I plus 1 elements. And now we'll be maintaining j as the next element we can add from the right. And we'll be shortening our prefix and lengthening our suffix. So while there are still some letters in our prefix, we remove the rightmost letter from the prefix. And now maybe the counts are no longer sufficient. So while the minimum of our values is less than k, we have to add elements from the right. And of course we don't want to cross over I, that really doesn't matter, but it never really hurts to write checks like that. We add the element at position j, and of course we move the right pointer to the left. And after this while loop, we are again sure that we have k of all elements, so we update our result with the minimum of the previous result and the number of elements that we have. We have I plus 1 elements from the left and n minus j minus 1 elements from the right. So the plus 1 and minus 1 disappear, is just I plus n minus j. And at the end we just return the result. So this is the implementation that looks explicitly at prefix and suffix. It's also of course possible to look explicitly as a subarray. Whichever you prefer, feel free to write it.